the quality of the welding. Okay, so and one I'll talk about it later. Okay, so this all right. So we move on to this video.
The selected welding method must be able to ensure welding quality and meet the technical requirements of product design. At the same time, it can improve welding production efficiency, reduce manufacturing costs, and improve working conditions. According to the material performance and structural characteristics of the product, according to the characteristics of various welding methods, combined with factors such as the production type and production conditions of the product. It is selected after a comprehensive analysis. Pay attention to thermal conductivity, electrical conductivity, melting point, and other properties of the base material. For metal materials with high thermal conductivity, welding methods with large heat input and strong penetration ability should be selected. For heat-sensitive materials, welding methods with low heat input are easy to use. When welding, all welds on the weldment without displacement, four different positions of welding, including flat welding, vertical welding, horizontal welding, and overhead welding, will be adopted because the welds are in different spatial positions. Usually, the welding material is selected according to the nominal guaranteed value of the deposited metal, and the actual strength of the deposited metal is often much higher than the nominal guaranteed value. If the metallurgical factors or the fusion ratio are considered, the strength of the actual weld metal will be far, far higher than the nominal guaranteed value of the deposited metal of the welding material. Desire is low strength, matching reality may be equal strength. Desire is equal strength, reality may be super strong. For the weld metal of heat-resistant low alloy steel and high alloy steel, the chemical composition or corrosion resistance should be guaranteed under the premise of ensuring the mechanical properties. The actual meaning of guarantee is chemical composition for chromium molybdenum steel, but for high in terms of alloy steel. The corrosion resistance should be higher than or equal to the lower limit of the value specified in the corresponding base metal standard or meet the technical requirements specified in the drawing. Manual arc welding is currently the most commonly used welding method. It is also widely used. According to different welding procedures, structural steel, low-grade steel, stainless steel, and non-ferrous metals can be welded. Submerged arc welding is mainly suitable for the welding of longitudinal circumferential seams of structural steel, low-grade steel, and stainless steel medium and thick plates.
Okay, if you notice that there are some of these MIG, basically is they put, even though it's a consumable electrode, however, they use this wire rod, right? You can see they use the wire in the video just now. So sometimes when you are about to cover this, let's say there's a big hole, you know, and so on, whereby you require a lot of this metal. So this wire rod basically act as this extra material or give more materials rather than you consume the whole rod, you know, just to fill up the hole, you know, and so on. All right.
Tungsten argon arc welding is mainly.
All right, just now you see here, there's a big hole here. So rather than joining, you have to fill in this hole as well. So whereby they use this extra rod here to provide, okay, to supply them with more metal for that for it to be melted and then fill in the particular hole.
Used for bottom welding of stainless steel, non-ferrous metals, and high-pressure pipelines in power plants. With welding, all the metal materials mentioned above can be welded and can realize welding automation. The current welding robot uses MIG welding. The selection of welding wire should be based on comprehensive considerations such as the type of steel to be welded, the quality requirement.
So you see that the quality actually, the welding actually is of a very clean, okay? So very clean welding is obtained, whereby you can see from just from the color is there's no outside contaminations, and so on. Okay. Normally, if there is any contamination, you will see some bluish, grayish, kind of colors, and purplish, kind of colors actually reflected on the surface of this metal. So this simply because that this process basically is with the use of inert gas. So this inert gas, like I say, is provide a shield so that no oxygen will be able to come in. All right. So that's why there is oxidation or scaling of this surface actually is made impossible.
The welding parts, the welding construction conditions, plate thickness, groove shape, welding position, welding conditions, post-weld heat treatment, and welding operations, etc., and cost. Choose welding according to the steel type of the structure to be welded. For carbon steel and low alloy gold high strength steel, it is mainly based on the principle of equal strength matching to select welding wires that meet the requirements of mechanical properties. For heat-resistant steel and weathering steel, the main focus is to consider the consistency or similarity of the chemical composition of the weld metal and the base metal to meet the requirements for heat resistance and corrosion resistance. Welding process performance includes arc stability, spatter particle size and quantity, slag removal, weld appearance, and shape, etc. For the welding of carbon steel and low alloy steel, especially semi-automatic welding, the
Hi, I'm John Swartz from Miller Electric. Throughout the course of a year, we get an opportunity to attend many events and shows and interact with our customers to talk about the TIG welding process. When we do, there tends to be a pretty common theme of questions that we get, so we wanted to take an opportunity today to go over some of the more common ones we get. So we're going to cover topics in today's video, like what is the proper angle for holding your torch, how do you prepare your tungsten, and we're going to talk about some tips and techniques to help you improve your stainless steel TIG welding. So let's get started. The first topic we wanted to cover is proper torch angles. The first thing I usually tell people that have issues with the TIG welding process at most of these shows is if you just keep 3 simple things in mind with the TIG process, it'll probably solve a good 80 to 90% of your application issues that come up. It really boils down to angle of your torch, the angle of your filler material as you're adding it into your molten puddle, and just keeping in mind that the torch melts the base material and the molten base material melts your filler rod. To make things a little bit easier, here's a little snippet from the Diversion 165 and Diversion 180 DVD, maybe help clarify things a little bit more for you. Now I'm going to demonstrate the proper weld technique without initiating the I'm right-handed, I'm holding the right hand, and then work from right to left. And I want to position my torch within about 1/8 of an inch from the surface. Once I establish the arc, I'll tip the torch to about 15 to 20 degrees away from the direction of travel, which allows for better visibility of the weld puddle and accessibility of the filler material. I move the torch along the seam, making sure to keep it centered. If filler material is needed, I bring it in as low an angle as I can to help prevent hitting the tungsten and contaminating it. I progress the torch along the seam, adding filler material as necessary. So the next most commonly asked question we seem to get is, how do you prepare your tungsten? So here's another little snippet from the Diversion 165 and 180 DVD that talks about how to grind your tungsten regardless of what material type you're working on. So let's head over to the grinder and sharpen the tip. Before preparing the tungsten, make sure to read the owner's manual for recommended safety precautions and additional information for proper grinding technique. I have my grinder set up with a diamond grinding wheel. Tungsten is a very hard metal, and although a typical grinding wheel can be used, you won't be able to achieve as good a finish on the sharpened tungsten, and you will wear out your wheel sooner than if it were diamond. You will want to hold the electrode parallel to the wheel as opposed to perpendicular. This ensures that the grind marks are running the length of the tungsten rather than across it, and aids the flow of current down the electrode. With a steady grip, I slowly rotate the electrode to form a point, much like you would sharpen a pencil. I want a point that is no more than 2.5 times the diameter of the electrode. This is how we would prepare the tungsten for welding mild steel, stainless, and chromoly. However, for aluminum, we would add one more step. We would take the sharpened tungsten and grind off the tip to create a flat spot or land. When that is complete, we would place the tungsten back into the torch with the ground end sticking out approximately 3/16 to 1/4 of an inch. Now on to stainless steel. It seems like we typically get two pretty common questions when we're asked about that type of material. One, how do I make my stainless steel welds look better? And two, how do I prevent the warpage that seems to happen all the time when I'm welding this material? Here's a couple of examples that I can kind of talk through to show you how we can prevent both those situations. When it comes to the weld appearance and the warpage issues with steel, it really boils down to one key problem. Too much heat is being applied. And a good indicator of this is the color change the weld area goes through. Typically, we're shooting for a light straw to a nice salmon color. If you're getting those deep dark purples to a gray that looks dirty and heavily oxidized, that's too much heat.
All right. Now, this is the one that shows that this surface basically is somehow contaminated somehow. So you might ask, didn't you just say just now that the inert gas, will shield it from oxidations, and so on? Yes. The electrode, the whole system basically is, able to shield these oxidations, from happening. However, the filler wire actually being placed, at the stores, and so on is already being oxidized. And you use that filler wire to actually do this welding. So the oxidized filler wire will be melt together and then form, then you can see this kind of color. However, you didn't see that happen in this MIG process.
Not only does it not look good, but it also reduces the corrosion resistance of your stainless steel.
Because once you have the external things actually go in, so there is a tendency for these oxidations to happen rather than not happening. So there will be some mild, especially on the surface, some of it. So you can see, this kind of purplish. However, it's not that fatal. So the color is still okay.
Too much heat also has an effect on warpage. Stainless steel is unique in the sense that it doesn't transfer heat as quickly as other metals do. So again, too much heat in a localized area is going to make the material warp. How do we counteract that? It may sound simple, but just by simply reducing your amperage and increasing your travel speed will help decrease the amount of heat being applied to an area. Another little trick is if you reduce the diameter of your filler material because it takes less energy to melt a smaller filler rod. And because of this, you don't need to apply as much amperage. Hopefully these pointers helped out. For other Miller product information and other...
So that will be it for this welding of this MIG and TIG. All right, so I'm going back to our notes. Okay, the next three process basically is a very similar process, just the amount of energy and the intensity of the energy used will be different. One is called plasma, whereby high energy is being shoot out from this nozzle or this electrode. So whereby they use the non-consumable electrode to shoot out this plasma onto this welding surface or the area that you wish to perform the welding. All right. So another one is electron beam. Okay, you have this electron gun, so act as your electrode, and then it shoot out energy in a high, more focused beam. All right. So if you can see that this plasma basically is wider, the affected zone is bigger. All right. So the electron beam basically have a more focused beam. So maybe it will produce a cleaner welding, and then you can also produce, let's say, in a more perform the welding in a more confined space. Okay, because of this small amount of area only will be welded, a very minimum small area, okay, which make the welding possible. So as things goes on with the development of technologies, things are getting even smaller and smaller and smaller, and soon that they found out that this electron beam might not be sufficient anymore, so they come up with this, called this laser beam welding. All right. So, all right, let's move on to see this video.
Give me Teo Ice Limao.
Hey guys, welcome to SkillLink. Plasma arc welding. It looks like a very fancy name for a welding process. Plasma arc welding is a type of arc welding procedure which weld metals and materials. The working of this welding type is very similar to that of TIG welding. Normally, in TIG welding, a tungsten electrode is used to strike an arc between the welding apparatus and the workpiece. In plasma welding, the same thing is done, but in a different manner. We'll explain the whole concept by comparison. In a regular TIG welding torch, we have a tungsten electrode, the pathway for the shielding gas, and the handle for the user to hold it. When the power is switched on and the torch is brought close to the workpiece, an arc is struck. This is due to the flow of current. Electricity jumps from the electrode and onto the workpiece to close the circuit. During this, it ionizes the air in the gap. Due to the resistance air offers to the flow of current, the temperature of the arc increases. The bright and hot arc is also known by another name called plasma. Plasma is generally considered as the fourth state of matter after gases, liquids, and solids. A great example of plasma is lightning. Whenever there is a heavy downpour of rain, we often see a flash in the skies. This is nothing but partially iced gas which forms plasma. The specifics behind this are very complicated to explain in a single video, but this should suffice to give you a brief understanding on what plasma actually is. In plasma arc welding, the construction of the torch is totally changed to increase the temperature of the arc. The tungsten electrode is placed inside a specially designed nozzle that focuses a stream of inert gas moving at high velocity into a constricted and narrow path. When an arc is struck, the inert gas is forced to flow through the region of the arc. This causes the gas to ionize due to the electric arc and form plasma. The arc and the plasma then flow through a narrow constricted opening. The sudden decrease in the flow area increases the velocity and the temperature of the plasma arc. They exit the nozzle at almost the speed of sound and also reach temperatures of more than 13,000 degrees centigrade, hot enough to melt any known metal to mankind. Because of this, the torch is always cooled by circulating water through the handle. A very big advantage of this welding is that it can also be used to cut metal with very minor changes to the torch design. The shielding gas is replaced with an oxygen blast, which is used to chip away any metal oxides formed during the cutting process. The final cut is very clean without any unnecessary chipping. Although this method was developed way back in the 1960s, it is not widespread. The main reason being the high cost of the welding equipment. The torch also needs to be made with special provisions for water cooling due to the extremely high temperatures of the plasma. This makes it rather difficult to manufacture and ends up driving its cost up. That's it for today's video, guys. We'll meet again in the next one. Until then, bye.
Right, next we are going to move to the electron beam welding. Okay, so let's see which one. Okay.
你知道这是什么吗？你相信这个很酷的东西在亚马逊上面卖288.98美金？偷偷告诉。
In electron beam welding, the coalescence heat is generated by the kinetic energy of a focused stream of electrons directed upon the joint. The electrons are produced by an electron gun, accelerated to high velocity, shaped into a beam by electrical fields, and then further collimated or made parallel and focused by an electromagnetic lens. This electron stream is developed in high vacuum, but actual welding can be performed in either high vacuum, partial vacuum.
So you can see that the flare or the area that is being welded, is not as bright as the one just now, right? So it's a more focused kind of beam electron, this plasma welding, all right?
Or standard atmospheric pressure. Because of the intense and concentrated heat generated, total heat input is low, minimizing heat-affected zone size and part distortion. This also allows for the creation of extremely deep and narrow welds. Additionally, joints inaccessible by other welding processes can be welded. Virtually all ferrous and non-ferrous metals, thin or thick, can be joined. Welding speeds are fast, and filler metal is not generally required. Equipment cost for electron beam welding is typically high, and welding is generally limited to machined parts assembled in primarily butt, corner, and lap joints.
Okay. Next, we're going to see laser.
刚刚好融合。
Okay, you can see that the 2 mm. Okay, so it is very suitable to be used in some very fine spaces, confined spaces, whereby spaces are limited, kind of welding. So next, I'm going to show you this the very high precision type of welding by using laser. Okay, so this can't be achieved by some of the thing that you already learned so far, like for example, this arc welding, no, you can't do that, all right? And for those of you who can't actually tell the difference, okay, so maybe I'll show you this, what's the difference between this plasma, and so on. Okay, let's view this video.
Junky rundown shop, barn falling in, my daily driver, 180,000 miles, 280,000 miles. Nobody would ever know what we got going on in here. Look at that fiber laser doing work. Here is a comparison. These just come off the laser. Those just come off the plasma. You can see they're still wet. And then, so let's get a side-by-side comparison of plasma versus laser. So this is the front side. And let's get a look at the back. The holes I had slowed down by 20%. So pretty common, even with fine cuts, to get in the back of holes. I think right there is where it went over a slack. And then let's stand them up on the edge quality. And also the dimensions. I'm gonna get those lined up a little bit better. Well, I don't have them exactly lined up, but you can see, you know, it's plasma pretty good, pretty accurate. All right, here's a quick side-by-side review of plasma versus laser material. And that's the front side on the laser. You can see all of our bridges are intact, and those are 60,000th bridges.
If you can see clearly, this is laser and that is plasma. If you can see from the reflection of the surface, right? So this one looks a lot more clean, you know, and so on. And just now it shows you the side way of it. You can see that the surface is somehow, one is being more smoother and the other one is being more rough, you know, and so on. All right. So that's one of the difference because of the, let's say, the zoom in. Okay, the zoom in, the more focused beam actually is produced in a laser, so that only a very tiny bitty places or this area actually is affected, rather than a bigger zone is being affected by this welding operation. So in the end, so the quality might be a little bit different.
The back of it. I know this sheet had a little, you know, was just a scrap piece I had laying around, and it's got some rust and stuff on the back. I did run it through the belt sander, and we did use the same piece on both, but by running the sheet through the belt sander and putting a grain on it, you can see right off the laser, you could paint that, do whatever you know, powder coat it, whatever, bend it, heat treat it, whatever you're ready to do. So this is the plasma, and you know, you can see in a few areas it almost nipped the bridge away, and then other areas it completely blew it away. Again, a 16th, no, it might have been I can't remember what the bridge was on it. But that's the back of it, and you can see, you know, it really doesn't make any sense to pre-grain cold rolled or anything on a plasma because you have a lot of cleanup work to do. You know, get it cleaned up, and then on the back of it there, lots of dross. Now these, I've seen guys take them, and you know, by the time you get them twisted and bended up, that dross will come off while you're doing that. Depends on how you decide to finish these. But you know, in this particular case, but you may be working on something else where you're not bending it. And dross, even though it's not a lot in some areas, you know, are pretty clean. The areas that do have dross, that dross is on there pretty hard. And being able to hold that thin material while you're trying to grind it and all that, man, just, it's not a good solution. This is really where the laser, in my mind, really shines over plasma. On thicker materials, you know, 1/4 inch steel, whatever, I mean, you have a hard time finding much of a difference. There is a difference, but this is where it really stands out.
Hello， 你好，你有买股票吗？如果有的话，请不要走开，因为我在这里。
All right, guys, check this out. I'm going to do a little voiceover here real quick while these are cutting. I wanted to point out that the lift height on both the laser and the plasma is set to 2 inches. But if you notice on the laser that, you know, the short moves between each of those holes, the main difference is that the retracts and rapids.
So you can see from here that this one produces a bright beam, you know, to produce sufficient energy, whereby this one is just, you know, some minus, very tiny, small sparks, you know, and so on. All right. So that's one of the differences between these two. So it depends on, not to say that the plasma is not good. So depends on the job that you intended to do. All right.
Simultaneously, where the plasma does its full retract, and when that's complete, it rapids and then plunges to pierce the next hole. So these are both cutting at the same speed. That rapid, the acceleration, and the combination of the rapiding and retracting at the same time really is what makes the difference. So you'll see in a minute that the you know, we'll kind of fast forward here and get you to the end of this, but the laser completed this in 4 minutes and the plasma took 14 minutes roughly. All right, here you go, the comparison of laser versus plasma on this aluminum. And that's right off of the laser backside. I think I can tweak these settings in just a little bit. There's a tiny little bit of a raised area. I mean, I don't know if you can pick that up on camera or not. You can feel it just a tiny bit when you rub over it. Also, I did not do a lead in on any of this, so you can barely see the pierce on each one. So I probably shouldn't run a lead in when I do these as a production run. Here's the plasma. There's no book specs for this particular combination. Fine cut consumables, 90 thousandths thick aluminum, 3/32. And but I have good luck with this setup, 170 inches a minute. Now I will say on the inside cuts and holes, I had those slowed down at 60%, but the outside it cut 170 inches a minute. This was 175 inches a minute. So you can see.
You can see, especially on the edges there, there's some sort of like, give you like this, the edgy, you know, where if you really touch it, you feel something that is rough, okay, on especially the edges, the radius area, okay, whereby it feels like it's not being properly cut, okay. Other than besides that, welding techniques, like for example, like this beam, is not just able to actually join material. You can use it to cut material as well.
Some detail loss on the.
Now you can see that there's a detail loss. Somehow it doesn't feel like it's doing the job very nice. So the smaller it is, okay, the diameter of this thing, the smaller profile of these products, that you use. If you use this plasma, and so on, this is what you are going to end up, because it's not really that focused, okay, and then the heat affected zone is huge. Okay, so it might affect the other edges, okay, during or when this operation is being carried out.
These little features here, they don't have exactly square edges like the laser cut does. But I don't know if that's important on this or not. I'm going to send both of these to the client and see what they. Oh, the crap flap! Check it out, guys. This is a KTM 790. That aluminum part is going to go on. They come from the factory with an opening right there, and you can see the part there. The prototype I sent them is fitting in that spot pretty nicely. They did a great job on the design, fits the overall theme great. And I tell you, I'm excited to be working with these guys because they're just like me. They're trying to make it happen. They're marketing these accessories and things through their website, motopumps.com. And obviously, the more they grow, the more I can grow. So check them out at motopumps.com.
Okay, all right. All right, we'll move back to these notes. All right. Next, we are going to move on to this thing called the resistance welding. All right, so this thing actually explore greatly on the resistance properties of this metal. Okay, so as you know, that metal, they have their own resistance. Okay, especially when you connecting it to the electric current. Okay, some is a very good this electric or the currents connectors, some are not. Okay, so this thing actually affect, or this thing or this process basically explore fully on the resistant properties of this metal. Based on this property, and then they develop this thing called H equal to I square RT. So whereby H is the heat generated, I is the current, R is the resistance, and then T is the time. Okay, so the most famous one actually is from this most of the product being used in the automotive industry is called the spot welding process. Okay, so spot welding process, basically you have two electrodes, one at the top, one at the bottom, and then you compress or you put near to two pieces of metal. Okay, and then when the current is on, So there will be the flow of electron towards through this metal. Okay, and then you apply some pressure. Okay, apply some pressure. Okay, and then they will form a certain weld nugget on top of, in between, not on top of, in between this actually these two pieces of metal. Okay, let's see how it works. All right.
Resistance welding is a process where metal parts are squeezed between the weld tips. Current flows between the weld tips and encounters resistance at the weld tip interface and at the part interface. Resistance to the current at the part interface creates enough heat to melt the metal and cause a weld nugget to form. When the weld gun closes, the weld tips contact the metal and squeeze them together. The metal is squeezed for a short time to make sure that the weld gun is fully closed and that the full weld tip force is achieved. This is referred to as squeeze time. A squeeze time of about 12 cycles is used for small weld guns, and 25 to 30 cycles are used for larger weld guns. When the squeeze time is complete, electric current begins to flow through the metal from one weld tip to the other. The duration of the current flow is referred to as weld time. The current generates a lot of heat when it encounters the resistance at the part interface, and a lesser amount of heat at the weld tip interface. The heat at the weld tip interface is conducted away by the water-cooled weld tips, while the part interface continues to get hotter and hotter. About halfway through the weld time, the metal at the part interface begins to melt and a weld nugget is formed. When the weld time is complete, the current stops flowing. Then a hold time of approximately 4 to 5 cycles is used to give the weld tips enough time to absorb heat from the outer perimeter of the weld nugget and cause it to harden before the weld tips open. A weld nugget should be as wide as the weld tip that contacts the thin metal and penetrate to between 20% and 80% of the metal thickness. This is referred to as a setup nugget. To produce setup quality weld nuggets, you need to understand how resistance welding is affected by weld tip alignment, weld tip force, squeeze time, weld tip size, weld current, weld time, weld tip cooling, and hold time.
The operation of resistance welding is shown in this video. Tom, copper electrode. The metal parts to be welded are placed between the electrodes. When the current passes through the electrodes, the electrical resistance at the metal joints becomes very high. So, the metals are brought to red hot plastic condition. Now mechanical pressure is applied to complete the weld. Types of resistance welding. The different types of resistance weldings are shown in this video. Seam welding, upset butt welding, spot welding, projection welding, flash butt welding, seam welding. In seam welding, the welding electrodes are motor-driven wheels rather than stationary rods. The result is a rolling resistance weld or...
Okay, this thing is called a seam welding, whereby the electrode is made into the wheel form. so that when the metal actually, that you can see that this two piece of metal is flowing through it, then the roller is rolling, means that these two pieces of metal is continuously being welded rather than leaving the spot to create only the nugget. This one is a continuous nugget overlapping each other, so that the whole place is being well seamed. Okay, where you can see this product of this seam welding. Now, if you would actually look into this beverage drink that you have, you will notice that there are two types. One is the one that like for example the Coca-Cola, and so on. Another type, you can notice the difference. Another type is the like for example the non carbonated type. Like for example, air kekwa, there's the soya bean, the coffee, and this Milo kind of canned drink. You can see that this surface basically is a little bit different. Now let me look into Google. Okay, this okay, okay, too bad that this it only shows this good side of it. Okay, never mind. Okay, let's move back to the notes, right? So I'm going to draw a drawing for you. Okay, in this normally this the product that needs to be performed in seam welding is normally they use this metal, okay, and then what they do is that they will fold it into something. Oops, unfortunately I complete the circle. Okay, shouldn't be. All right. Okay, it should be something like this. Okay, and then this piece of metal will be something like this. Okay, so in the end, I wish to weld these two area. Okay, and however, you know that this is for drinks, right? So the drinks is something like this. Okay, and if I only weld, weld nugget, something like that. No, something like this. So it's not going to hold the water, right? So this water is going to leak through the non-welded area. So it's the best thing is that I weld through this whole thing here. So instead of just weld nugget, I produce a continuous weld nugget, weld nugget, weld nugget, weld nugget, weld nugget. Rather than this electrode, I use a wheel. The wheel will be rotating. Okay, will be rotating and this thing will be moving forwards. Okay, so that the continuous weld nugget is being produced rather than just a spot welding. So this is a resistance seam welding. So yeah, you can see from here, yeah, this photo is nice. Okay, so of course you can use this timer, and so on to produce, let's say, periodic welding. Okay, then you will produce a weld nugget, a series of weld nugget, or this current is flowing all the time, and when this thing is passing through, it will produce a series, a continuous, nugget. So it helps seaming it, to provide a seamless, all right, welding, so that you can use it for, let's say, this water tank, the metal water tank, and this beverage drinks. Okay, like for example, this like I mentioned just now, your coffee, your Nescafe, you know, Milo, okay, and your the Kikwa drinks, you know, soya beans, you know, and those that is non-gases. All right, so normally they use that. All right. So we move back to our video.
Non-hermetic seam weld used to join two sheets together. Upset butt welding. Upset butt welding is a welding technique that produces coalescence simultaneously over the entire area of abutting surfaces or progressively along a joint by the heat obtained from the resistance to electric current through the area where those surfaces are in contact. Spot welding. Workpieces are held together under pressure exerted by electrodes. Typically, the sheets are in the 0.5 to 3 mm thickness range. Process uses two-shaped copper alloy electrodes to concentrate welding current into a small spot and to simultaneously clamp the sheets together. Projection welding. Projection welding is a modification of spot welding. In this process, the weld is localized by means of raised sections or projections on one or both of the workpieces to be joined. Flash butt welding. Flash welding does not use any filler metal. The pieces of metal to be welded are set apart at a predetermined distance based on material thickness, material composition, and desired properties of the finished weld. Current is applied to metal, and the gap between the two pieces creates resistance and produces the arc required to melt the metal.
Okay. So next we are going to move into this a different approach in this welding process. All right. So previously we learned all about this fusion welding. Okay, produces the source or the energy source is the electricity. All right, we use the electricity to produce the heat. Okay, provide electron jump by the exploring the resistance, you know, by using laser, okay, electron beam, and then the plasma or electricity. All right. Now, the next one that we are going to cover, okay, is with the use of gases. All right. So means that it's by the use of hydrocarbons. Okay, means that there's a flammable gases to produce the heat. Okay, let's look at the video first. Okay, before we come back for more.
Gas welding. Gas welding is a welding process that melts and joins metals by heating them with a flame caused by a reaction of fuel gas and oxygen. The most commonly used method is oxy acetylene welding, due to its high flame temperature. In this video we will cover the following about gas welding, equipments of oxy acetylene welding, working, advantages, disadvantages, and applications. If you are new to this channel, click on the subscribe button and turn on all notifications so that you will never miss an update. Gas welding equipments. Cylinders. In gas welding, there are two cylinders. One is a fuel gas and is of maroon color. The second one is oxygen gas and is black color. Oxygen and acetylene are stored under pressure in a steel cylinder. They are seized by the amount of oxygen or acetylene that they hold. Cylinders should always be secured and used in the upright position. When a cylinder is not being used, the valve cap should always be in place. Oxygen cylinders. They contain compressed oxygen at high pressure, that can be as high as 2200 psi. All cylinders have valves, and are fitted with a screw-on steel cap that protects the cylinder valve when the cylinder is not in use. Acetylene cylinders. These cylinders contain acetylene under pressure, made of steel and have cylinder valves. The cylinders contain porous filler material, which is fitted with acetone, that allows the acetylene to be safely contained in the cylinder at 250 psi. Acetylene should never be used at a pressure that exceeds 15 psi, as it becomes highly unstable, which, depending upon the condition, could cause it to decompose and explode. Pressure regulators. For welding, the oxygen and acetylene are required at low pressure, but in the cylinders, they are filled in high pressure. So a pressure regulator is required to control the pressure of oxygen and acetylene before reaching the mixing chamber. Torch. The torch consists of the handle, oxygen and the fuel gas valves, and the mixing chamber. Inside the handle, there are tubes through which the oxygen and fuel gas flow. Mixing chamber. In this chamber, oxygen and fuel gas are mixed. In this mixing chamber, the ratio of oxygen and fuel gas is mixed according to the type of flame required, such as neutral, oxidizing, or carburizing flame. Control valves. There are two control valves available in this torch. One is for the oxygen, and the second one is for fuel gas. These control valves are used to control the flow of oxygen or fuel gas to the mixing chamber. Gas hoses. The gas hoses are used to transfer oxygen and fuel gas from the cylinder to the welding torch. These hoses are color-coded for easy identification. This color coding varies from country to country. Nozzle. The mixture of oxygen and acetylene comes out of this nozzle. The mixture of these gases comes out in pressure from the nozzle, and then is ignited by the striker. Goggles and gloves. In gas welding, goggles and gloves are used for the safety of the operator who does welding. They are used to protect the hand and eyes of the welding operator from radiation and heat of the flame. Working of gas welding. At first, all the equipment of gas welding is fitted properly and carefully. After that, a regulated pressure of gas and oxygen supplied to the torch where they are properly mixed. The mixture.
Okay, there's a term that been mentioned about radiation. Now, this radiation is not the radiation from radioactive substance. No. This radiation is the meaning of it is the heat being transferred, okay, from the welding zone through radiation. Means that it's spreaded. The heat actually spreaded around that particular zone. Now, typical radiation activities happen every day, whereby from the sun, okay, the heat from the sun actually convey to us or to Earth, okay, through a process called the radiation. Okay, means the heat is moving by a certain radiation wave, okay, that reaches the Earth. All right. So here you have to wear this protective glove, and so on, the protective shirts, and so on, to prevent this, let's say, this heat being exposed or being subjected directly to the welder or to the operator that performed the welding operation.
Mixture of fuel gas and oxygen is then ignited by the striker. Then the flame of the torch is controlled by different valves present in the welding torch. Based on the type of flame required, the valves are operated accordingly. If the neutral flame is required, then both the valves are opened equally. If the oxidizing flame is required, then the valve of oxygen is opened more. And if the carburizing flame is required, then the valve of the fuel gas is opened more. The flame is set as neutral, oxidizing, and carburizing based on the metal, its thickness, and some other welding conditions. If you want to know about types of flames in detail, the link will be provided in the description of this video. After that, the flame of the welding torch is moved along the line between the two metal plates. Along with the metal plates, a filler rod is also used, which is used to create a pool of molten material that will fill the gap between the two metal plates interface. The filler rod is moved along with the flame. The filler rod is kept at an angle of 30 degrees to 40 degrees, according to the welding technique being used. After moving the flame and filler rod along the line of two metal plates interface, the two metal plates join together because of the melting and solidification of metal plates interface and the filler rod. Advantages of gas welding. 1. It is easily portable. 2. It is very less expensive and
Easily portable here means that it is really portable. Okay, when you are performing, like I mentioned in the earlier stage of this chapter, that this particular gas welding, this particular welding techniques, basically you can perform the welding almost everywhere, anywhere. Okay, means that you do not have to, go and find electrical source, power source, and so on. You can perform it in the jungle. You can perform it, in your garage, in everywhere, whereby this, let's say, this electrical power is not accessible to you, not available. Okay, so all you need is to have two cylinders, one with acetylene gas, one with oxygen, and then a welding torch, and then let's say a lighter or so on to start this sparks and start the burning of producing the flame for actually these joining operations or these welding operations. Okay.
and very affordable. 3. It can be easily maintained and repaired. 4. It is a very simple piece of equipment. 5. It is self-sufficient and does not rely on other equipment. Disadvantages of gas welding. 1. The metal joining rate is very slow, so the welding speed is low. 2. A skilled operator is required to operate this machine. 3. The power density is low. 4. The heat affected zone is large. 5. Gas welding is not recommended for welding reactive and refractory metals. Linear applications of gas welding. 1. Used for joining thin materials. 2. Used for joining ferrous and non.
And another one that I can think of is that okay, as you see from the video just now, that there's a two nozzle. Actually, you can actually control the flow of acetylene and control the flow of oxygen, whereby the right ratio, okay, of oxygen and acetylene gas is actually you have to mix it. Okay, so beware of applying or supplying too much oxygen into this welding, because when you have too much oxygen, you know what will happen, right? Because there are already oxygens in the ambient, and then you supply even more oxygen throughout the system, means that the surface will get oxidized pretty much easy. It's just like party, you have so much oxygens in the ambient or in the surrounding of this heated zone of this welding, means that the oxidation tends to happen even more easily. All right?
Non-ferrous materials. 3. Gas welding is used in sheet metal fabrication. 4. It is used in aircraft industries. If you like this video, click on the like button, and if you are new to this channel, consider subscribing this channel to get all the latest updates.
I discovered a leak in my Oxy Acetylene lines that I think I just fixed. The Oxy line was pretty bad, but the acetylene also had a small leak that took some soapy water to find down. I should probably change these lines out altogether. These aren't that expensive. Maybe $1 or $2 a foot, depending on the size. At any rate, a lot less expensive than blowing yourself up. Maybe a bit more hassle, but definitely less expensive.
Have you heard that it is more expensive actually to blow yourself out? So one of these hazard, okay, of this or this dangerous thing performing this is that acetylene gas is highly flammable and even explosive. Right? So the risk is there. So heavily, the safety actually should be maintained. Okay, because we do not want to the cylinder to leak, and caught fire and in the end explode. It's just like a bomb there. Okay, because it's in the cylinder. All right. So That's why this guy is actually fixing or changing the pipe because he senses that there is a leakage in terms of this pipeline.
So since I have all this stuff out, let's talk about Oxy Acetylene, shall we? Before I got the TIG, this was my go-to welding rig for small stuff. Now it's mostly relegated to heating and bending, brazing, cutting, and just general burninating and melting. Before we get into the business end of things, let's take another look at the bottles. Let's start there. Ignore that bottle on the left. That's nitrogen, N2. I use that to fill my air guns. You're looking at oxygen in the middle and acetylene on the right, the short one. Notch. Do you know why acetylene is called acetylene? Do you know why it smells the way it does? Well, neither do I. But what I do know is, just like my boy, it's chained nice and solid to the wall. They're not just sort of floating around, hanging back here in the dark part of my shop on their own, where a yank with the hose or a bump could knock them over. If there's anything you take away from this video, is that Oxy Acetylene and high pressure cylinders in general have the potential to be extremely dangerous, but they're safe if they're used with caution, common sense, and you play by the rules. Let's start with oxygen. Oxygen is a gas, and a new bottle is usually filled to about 2,000 psi, give or take. That's about 140 bar, and that's a lot of pressure. To get that down to something we can work with, we need a regulator. A regulator is the thing that looks like a clock stuck to the top of the tank. Welding regulators have two gauges. Usually the one closer to the valve tells you the pressure in the bottle, or the cylinder as the pros call them. You can tell I'm not a pro. The other gauge tells you the working pressure coming into the hoses. Welding regulators are adjustable. You turn the knob, change the working pressure, easy peasy. My oxygen is currently set to about 5 psi. The regulator is regulating high pressure oxygen, 2,000 psi for a new bottle, down to 5 psi. Now let's have a look at the acetylene. In the bottle, acetylene isn't a gas. Well, it is, but it's dissolved in a liquid. It's dissolved in acetone. Well, it's complicated. Acetylene is unstable above 15 to 20 psi or so it can't be shipped on its own like oxygen is. I've got my Craftsman X-ray inspection tool. Let's have a look inside. Inside the steel shell of the cylinder is a porous matrix, kind of like that big hard sponge you have in the utility sink. You really should throw that away. It's getting kind of gross. The matrix is filled with acetone. Don't quote me on this, but it might be about 50% acetone. The acetylene gas is dissolved into that acetone, sort of like CO2 is dissolved in your soda before you open it. That makes sense? When you crack the can open, the CO2 starts to bubble out. That's more or less what happens with acetylene. That's what keeps it stable. That, by the way, is also the reason you should never use acetylene bottles on their side, or after they've been laying on their side, like in the trunk of your car. You should let them settle overnight or so. Now, I know there's someone out there right now commenting that they've used their acetylene bottle completely upside down, hanging from their ceiling for the past 30 years, and nothing bad's ever happened. The point is, you shouldn't do it. It's very dangerous. Anyway, just like the Oxy bottle, this also has a regulator. The scale is a little bit different because of the operating pressures of acetylene, but it's the same principle. And again, mine is currently set to about 5 psi. My rig is actually a little bit big for the kind of stuff that I do these days. So honestly, I've never really done very big work. I mean, this is by no means a big torch, but I would love one of those little mini Oxy Acetylene torches. The good ones are just so dang expensive though. But these things are so versatile, I wouldn't be without them. I mean, if you've ever watched the A-Team, you know just how multifunctional and critical an Oxy Acetylene torch can be. In order to provide you with the absolute most bang for your YouTube buck, and to stretch the soup a little bit, let's get a smidge techie here. Let's get into the numbers. Now, just like the Wonder Twins, acetylene and oxygen on their own are absolutely marvelous. But you put them together, that's when the magic happens. Acetylene is C2H2, and oxygen is O2. When you put those together and burn them, like any hydrocarbon, you get carbon dioxide and water, CO2 and H2O. I'm sure you probably get all sorts of other weird stuff, but the majority will be CO2 and H2O. What we just wrote here is a bit of an equation, but if you look close, both sides aren't balanced. We have more C's, H's, and O's on one side than we do on the other. Hey, that reminds me of that old joke. How did it go? What did the baby acorn say when it grew up? Stoichiometry. No, wait, I told that wrong. What did the baby Russian acorn say? I don't know. Let's move on. Let's see what happens when we try to balance our checkbook here. It's been a while, but we'll start with the O2. That looks easy. It's sitting there all by itself. Now, on the left, we have one O2, 2 oxygen atoms. On the right, we have 2 in the carbon dioxide and 1 in the water. So there's 3 there. We can't add another oxygen by itself on the left, so let's double the H2O, just to even it all out. Now we have 4 oxygen on the right. We'll add a 2 on the left to get us 2 O2s. So 4 oxygen atoms on the left, 4 oxygen atoms on the right. And when we doubled that water, we also doubled the hydrogens. So let's double the number of hydrogens we have on the left. 2 H2s on the left in the acetylene, and 2 H2s on the right in the water. So now what happened? We've got the oxygen sorted out, we've got the hydrogen sorted out, but when we doubled the H2s on the left, we also doubled the carbons. We essentially have 4 on the left in the acetylene and 1 on the right in the CO2. So let's put 4 carbon atoms on the right-hand side to match the 4 carbon atoms on the left. Just like before, we fixed the carbons, but we broke the oxygens. On the right, we now have 4 O2s from the carbon dioxide and 1 O2 from the water, for a total of 5 oxygen pairs on the right. Let's just change our 2 to a 5, and I think this thing's worked out now. We have the same number of carbons, hydrogens, and oxygens on the left than we do on the right. Now, if you're wondering why I went through all of this, I can't blame you. But take a look at what happened. In order to get complete combustion of the acetylene and the oxygen, for every 2 parts of acetylene, we need 5 parts of oxygen to completely burn it. And if we set up our torch to do that, to sort of meter those proportions of acetylene and oxygen, we end up with what's called a neutral flame. And we'll see that in a minute when we light her up. A neutral flame produces carbon dioxide and water. Alternatively, you could adjust the torch so you have an excess of oxygen or an excess of acetylene. If you have too much oxygen, you have an oxidizing flame. If you have too much acetylene, you have a carburizing flame.
你知道任何人都可以在短短10年内安全的获得10倍的投资回报吗？这意味着。
All right, well, we're not quite down to brass tacks, but we are almost cooking with gas. I picked up some new tips for my torch. Tips can be cleaned with a special tip cleaner, but sooner or later they wear out and you need new ones. Tips are sized by orifice diameter, either the size of the hole or some made-up number, like a number 2 or a number 4. The local shop didn't have all the tips that I needed, but he did have this sweet-sized nozzle at a really good price. I think I'm going to get to like this one. It's now my smallest one. What you're looking at is 3 nozzles for heating and welding or brazing, and a cutting head. We'll get to this later. The largest one you see here is the one that gets the most use, at least for me. For heating and brazing, you kind of want a large, soft flame instead of a needle-like pinpoint you might want for welding. Let's get the small one on and light it up. Now the torch has 2 knobs on it, one for each gas, and I'll be using these to adjust the balance for the flame. And because this is a smaller tip, I've also dropped the pressure at the regulators. The working pressures you set on the regulator are based on the tip or the nozzle, and that's sort of based on the work you're trying to do. The bigger the work, the bigger the tip, the higher the pressure. Check the literature from your torch manufacturer to find out exactly what pressures those should be. Those are very important to both your safety and having a good time with one of these things. You should use a striker to light up your torch. I've always been taught not to light a torch with an open flame, like a lighter, for example. And I'm not exactly sure why that is, to be honest. If anybody knows the sort of official reason, I'd love to hear about it. The only thing I've ever been able to think of is maybe the torch pressure could blow out your open flame. Like you try to light your torch with your lighter, and it just blows the lighter out like a birthday candle. Then you might be in a situation where you've got your torch, putting out a deadly mix of acetylene and oxygen, and you're, trying to strike your lighter back up. Anyway, I'm going to light just the acetylene. I don't know how well you can see it, but there's a lot of soot coming off of that flame. That's all carbon.
So this the video show
What you're looking at,
this the just now it shows a yellowish flame, right? So this carburizing flame, whereby the phenomena is that you have more acetylene than the oxygen, means that there is a lot of this hydrocarbon unfinished, okay, in combusting, okay, in burning. So whereby a lot of this hydrocarbon and especially the carbon being released. Okay, so that's why just now he's trying to burn this table, and then it ends up, all the black stuff, actually the carbon actually deposited on the table. So that's an indication on this the high carbon content residue actually left in the combustion. All right. So the neutral flame is just nice. All of these hydrocarbon, okay, the acetylene and oxygen, just nice, finished combustion, clean. All right. And another one is with the excess of oxygen. Of course, with the excess of oxygen, all the acetylene will be finished combusted. Okay. So, but however, with extra oxygen, all right, we got excess oxygen, right? Okay, so you can you can adjust, or you can control the ratio of this acetylene gas flow and the oxygen gas flow that is going to mix in this combustion.
here is the acetylene flame from before, no oxygen. And you're looking through a pair of welding goggles. You're going to start to slowly open the oxygen up, and you may or may not see 3 flame cones in there. The outer cone, the inner cone, and the smallest one nearest the nozzle. I can continue to open the oxygen until that middle cone and the small cone sort of become one. Right there, our checkbook is balanced, and we have a neutral flame. This is the flame you'd use probably 99% of the time. Now, there's something else going on here you may have never thought about. The flame is conveniently staying put. It's attached to the tip of the nozzle. Now, what's happening is there's a flame front. The flame is trying to burn its way up that gas. Sort of like when you light a fuse, the fire, it would run up the fuse. The flame isn't moving because the gas is coming at it as fast as it's trying to burn it. In our fuse analogy, the fuse is moving closer to the fire at the same speed that the fire is trying to climb up the fuse. So we have a bit of a balancing act. The gas coming out the nozzle at a certain speed, and the flame trying to burn its way back into that gas. If the pressure is set too low on your regulators, you could end up in a situation where that flame speed exceeds the speed of the gas, and the flame comes into the nozzle, comes into the torch. It starts to burn its way up to that fuse, back to the bottles. That gave me chills just saying that out loud. The term for that is flashback. And in your lines, at some point, maybe 2 points, you should have installed flashback arresters. These are basically like thermal check valves that should break the link if a flame makes it this far back in the tubing. So my hoses are springing more leaks. The guy at the welding supply laughed at me. You know, I was in there not 2 days ago. The guy said, "These nozzles look pretty old. Sure your hoses are still okay?" And I said, "Yeah, I want some cheesy poofs. Yeah, my hoses are still okay. Don't try to upsell me. I'm not an idiot." So I went in, got new hose, and he upsold me on new flashback arresters. So all kidding aside, what I'm really trying to do here is maybe provide some additional insight, some information you might not find in other videos. There's literally a ton of videos on YouTube on this subject. And I know because I've waited. All right, so it's been a while, but I've got just some scraps of steel to try to lay down some welds. When you light the torch, start with the fuel first, with the acetylene. Some people like to open both of these so they're not getting as sooty a flame and making a mess, but that's actually quite dangerous. The acetylene on its own, at the pressures we'll be welding with, isn't as dangerous as an oxy acetylene mix. To keep it from making such a mess, just open it up a little bit more. So small flame, pretty dirty. Give it some pressure, it starts to clean up. And like before, slowly add the oxygen. or reduce the acetylene to get the balance right, to get us to a neutral flame. I'd hope this would go without saying, but I'm going to say it. The flame is very hot. I mean, if you've never used an Oxy Acetylene torch before, you likely have no real reference for just how hot this thing is. You don't have to take my word for it. Let's see what the thermal camera says.
Hi, James Cheeley here with the world's best knife sharpener. Forget sharpening knives the old way. Have a look at this. I can take a knife.
Be very mindful of where you point this thing. I know, it'll be just a second. You just need that one thing a couple of steps away. You'll just put the torch down and be right back. If it's not in your hand, turn the torch off. Then you give it a minute to start the puddle, and just let the puddle tell you when it's time to move on or add filler. Maybe easier said than done, but that's the moral of the story. All right, that was actually harder than I remembered it. I actually did 3 in order to get sort of the shots you just saw in the video. Compared to the TIG torch, this thing weighs a ton. Feels like I'm trying to arm wrestle somebody while I'm welding. I still think Oxy Acetylene is the way to start. I think gas welding gives you a little bit more insight into what's happening and gives you a little bit more time to respond and develop sort of the skills in the eye to recognize what's going on and adjust for it. And I think it's a more intuitive sense of like heat control, the torch angle, stuff that happens lightning fast maybe with TIG and especially with MIG, but maybe that's just the way I came into the hobby. So I just put the cutting head on. It might look a little complicated, but there's really not too much to it. Anyway, same adjustments as before, acetylene and oxygen to get us to a neutral flame. And then there's an additional oxygen valve. Now, cutting requires a lot more oxygen than welding did. Even a modest sized tip like this, I don't remember the number exactly, but this will cut some ridiculous thickness of steel. Let's take a look at the difference between a welding head and a cutting head. A welding head has only one orifice on the center. A cutting head has a lot more than one. The 6 jets around the perimeter are sort of the preheat flame. That's where your heat's coming from. And the jet in the middle is oxygen. That's what will be doing the cutting. The reason this has holes all the way around that center point, the center hole, is to allow you to move in any direction with the torch. Like you can cut a circle by standing in one place without having to walk completely around your workbench. Now in my particular torch, I open the oxygen on the body or the handle all the way and let the one on the cutting head control the mixture. The button serves as a bypass. It steps right around that button and sends sort of your full pressure air through the cut. Just like before, you adjust the oxygen and acetylene balance to sort of reduce that inner cone to match, in this case, the 6 cones around the edge to get the neutral flame. You can push the button once or twice and see what the balance looks like when you have excess oxygen and tweak it if you like. The torch will and should sound a little more violent when you hit the lever and you start running higher pressure oxygen through that tip. Now, to be honest, I'm a little hesitant about doing this cutting here in my garage. This is going to shoot sparks everywhere. I've kind of barricaded the top of my workbench. I'm going to try to keep this to a minimum. But, what kind of video would it be if I didn't do any cutting? I'm going to start off by letting the jets heat up the work, sort of melt the steel. When I see a small puddle has started to form, I can hit the lever and start cutting. Here's a little interesting tidbit. Once that steel starts cutting, once it's started to melt, you technically don't need the acetylene anymore. I remember my instructor was particularly fond of doing that demonstration. As he was cutting, he'd cut the acetylene and finish the cut with just the oxygen. Basically, once the material gets to sort of that auto ignition temperature, the temperature where it would just sort of spontaneously burn, as long as you feed it enough oxygen, it'll keep burning on its own. When you make a cut with an Oxy Acetylene torch, you're basically making it rust very, very, very fast until it breaks apart in 2 pieces. And I didn't get into a lot of the very specific details. It was more about the torch and the torch setup. And maybe it helps make a little bit more sense of some of the terms and reasoning you might hear on other YouTube channels. I happen to really like Jody over Welding Tips and Tricks and would highly recommend his channel to anyone interested in welding or fabricating in general. All right, so what did you think of that? Did you learn something? Cool.
Okay, so that's it. Okay, so this for this oxy gas. So we'll be coming back on this chapter again, or this oxy fuel gas welding. All right, because I still haven't discussed about this the formulas. You know, I think it was mentioned in this video as well. So we'll come back in the next class. All right, that will be next week. All right, so that's all for today. Thank you very much, and then have a nice day. Have a nice weekend. All right, thank you very much. I'll see you.